In this section of Chapter 13, we're going to once again be looking at halogens and how they can interact with our double bonds. We'll be looking at a couple of different types of reactions with alkenes, alkynes, and we'll look at our halohydrons as well. So with this process, we're going to be looking at adding the halogen, the X2, across the alkene. The halogens that we're going to be looking at are specifically going to be limited to the bromine and the chlorine as halogens. We will not see this type of reaction with fluorine or with iodine. One of the other specifics associated with this reaction is that we're going to see an anti-addition of the two halogens to each other due to the intermediate bromonium or chloronium ions that we end up producing. So remember that anti-addition, if we're talking about it in Newman projections, they're 180 degrees from each other. So if we look at the reaction with our alkene and our halogen, the product is going to have those two X's anti to each other once we get to our final product, that is our alkane product. So when we look at this in terms of a mechanism, remember, the double bond is going to be the nucleophile. It is our electron-rich species, and one of the halogens in our X2 unit is going to be the electrophile. So we will see the nucleophilic portion come in and attack the halogen. But since that halogen contains lone pairs, one of those lone pairs is going to come back in and attack the carbon atom to produce that three-membered ring instead of the carbocation intermediate. We will then also see the bond break between the two halogens themselves. So the intermediate that we end up generating has the halogen as part of a three-membered ring. It has two bonds associated with it and two lone pairs, which gives it the positive formal 1 charge. So this is that bromonium or chloronium ion intermediate that we referred back to. So you'll notice because of that three-membered ring, it basically blocks one side. So when the second halogen, the halide, comes in as the nucleophile and attacks, it's going to attack from the opposite side. So you can kind of think about this as being very similar to an SN2 type mechanism, where we're breaking a bond and we're forming a bond at the same time, and that cannot happen in the same area. So we're going to break a bond on one side as we form a bond on the other side, which is why we see this anti-addition when we add in our halogens. Where it can also do is something very similar with our alkynes. So remember, our alkynes are those triple bonds. So if we have one equivalent of the halogen come in, it's going to form an anti and syn addition products. When we start looking at this in terms of the new alkene that we would be looking at. Reason being is because there is no bromonium, no chloronium ion intermediate, because we have the alkene, and we can't make that three-membered ring with the alkene. So the positive, the simplified mechanism, that vinylic carbocation that we would produce, we can see the second halide come in and attack from either side. But what we will see with this is because alkenes can still react with halogens, if we have excess of the halogen, we will produce a tetrahalide, meaning we are going to put as many of the halogens on as possible and get us all the way down to the alkane from the alkyne. So for our reaction with our alkyne, if we have a limited amount of the halogen, meaning we only have one equivalent of the halogen to go with our alkyne, we end up producing both the anti and we also end up producing the syn alkene. So anti is where we're going to see the two halogens add to opposite sides, like we talked about with the alkene going into the alkane, that nice anti-addition. Syn addition implying then that the two X groups are on the same side. They add to the same area. And this is just because of the mechanism and that we do not produce the bromonium or the chloronium ion intermediate like we did on our previous slide. What we will see though is because we did produce an alkene, if we have excess of our halogen, we will end up going all the way down to the alkane, which means we will end up with the tetrahalide final product. So we do have to be careful that it is very difficult to stop at the alkene, because our alkenes are also going to be reactive with the halogen as well. We can also produce halohydrins. So the halohydrin has both the alcohol unit and the halogen on adjacent carbon atoms. So with this, we're going to be adding the halogen and water to the alkene. So the X and the OH are what's going to be anti to each other. We are going to end up producing the Markovnikov product here, which means the nucleophile, that second nucleophile that comes in, which for us will be the water, is going to come in and attack the more substituted product. So if we look at our alkene, what is going to change is not only do we have the halogen, but we also have water in our reaction flask. We will end up producing the halohydrin, which gives us the halogen and the alcohol on adjacent carbon atoms. This is the Markovnikov's product. The second nucleophile, which is the water for us, will come in and attack at the more substituted carbon atom. That is our Markovnikov product prediction. So let's quickly look at our mechanism for this reaction. The initial mechanism that we start with is still going to be the nucleophilic alkene coming in and attacking the electrophilic halogen. At the same time that happens, one of the lone pairs on the halogen will come in and attack the carbon atom to form that three-membered ring at the same time that we break the bond between the two halogens. So this would get us to our intermediate that would be the chloronium or the bromonium ion. This then also produced the halide, the X minus. What is making this one different is now we also have water in solution. So we have two nucleophiles in our reaction flask. We have the halide and we have water. And the water is going to do the attacking to get to the halohydrin versus the halide coming in and attacking just due to kinetics. We're going to have a lot more water in our reaction flask than we will the halide. So just on the higher concentration, that's what's going to dictate what's going to come in and make our final product. So some of the byproduct might be that we will make some of our dihalide, but we're not going to have a lot of that X minus ion in solution. We're going to have a lot more water in solution. So the water will come in as the nucleophile and attack the more substituted side, breaking then that bond between the carbon and the halogen. So the initial product that we have here, we have our halogen and we have added water to our compound as well. So the last and final step is we do need to deprotonate the alcohol that we just added, so water can come in and do that for us, so that we end up with our halohydrin, as well as a little bit of acid in our reaction flask as well. So again, this is our overall mechanism of how we can get from the alkene to our halohydrin through the use of a halogen and water.